Hello, everyone. Yair, you can start.
Okay, sorry. Hi all. It is my great pleasure to welcome you to today's roundtable on metamaterials and metasurface applications. I am Yair Eran, VP Business Development, Ramot, the technology transfer company of Tel Aviv University. Metamaterials and metasurfaces are the forefront of material science, offering a new paradigm in manipulating electromagnetic waves. By carefully designing the structure of arrangement of their nano-sized elements on a scale smaller than the wavelengths of the waves they interact with, metamaterials can exhibit properties not seen in the nature. Metasurface, a subset of metamaterials, are two-dimensional structures that can control propagation of waves in unprecedented ways. Metasurfaces find application in antennas, beam steering, imaging system, spectroscopy, and more others. The field of metamaterials is continuously evolving, with researchers exploring new designs, materials, and applications. Today, we are pleased to introduce our leading scientist from Tel Aviv University, Professor Tal Ellenbogen and Professor Haim Suchowski. Unfortunately, Professor Jacob Scheuer doesn't feel well today and will not present this time. We wish him fast recovery. So, without further delays, we will move on to the first session. Professor Tal Ellenbogen is the chair of the Department of Physical Electronics at Tel Aviv University and heads the Laboratory of Nanoscale Electro-Optics. He holds PhD in nonlinear optics. He is Fulbright postdoctoral fellow at the School of Engineering and Applied Sciences at Harvard University, where he worked on nanoplasmonics and excitonics. In addition, he was a member of the Center of Excitonics in MIT. In 2012, he joined the Department of Physical Electronics at Tel Aviv University School of Electrical Engineering to establish the Laboratory of Nanoscale Electro-Optics. Professor Ellenbogen received several career awards and competitive research grants in the field of linear and nonlinear materials, including the Kadar Family Award for Outstanding Research, Schmidt Futures, ERC STG, and ERC COG grants. He heads the Center of Excellence on Optical Materials at Tel Aviv University. His research interests include nanoscale light matter interaction, nonlinear and ultrafast optics, and optical metamaterials. If there are any questions, please write them down using the chat, and Professor Ellenbogen will address them at the end of his presentation. Professor Ellenbogen, please share the presentation with all of us. The stage is yours.
Thank you very much, Eran. Two questions. One is if you see my presentation, and the other one is if you hear me.
Yes, we do.
Okay, so thank you very much for the nice introduction. Thank you everybody for joining us today. And I will present basically some of the developments that we had in the lab in the past few years on the capabilities and potential of using metasurfaces as flat optical elements, and also for active controlled teres generation. So for those who are not familiar with the metasurfaces, Eran presented them, but they are made out of engineered, basically, surfaces that are engineered in the optical regime at the nanoscale. So by engineering, we can basically functionalize the surface and mimic or create engineer artificial optical properties that stem from the engineering and not from the bulk. So we need basically to know, first of all, the interaction with the single elements, nanoscale element, which we can call also meta-atom. And these meta-atoms are made usually out of either metallic nano-antennas or high-index dielectrics. And we need to know how to design them. There are several ways. We can use our physical understanding, physical intuition, and there is also an emerging new way of using basically reverse engineering and machine learning, and I assume that Professor Haim Suchowski will address this opportunity later. So if we know the interaction with a single element, and also these elements scatter light, so they have a coupling and there is a collective interaction. If we know both the single and the collective interaction, we can then design and mimic macroscopic optical properties of refractive index, birefringence, wave impedance, polarization response, and even nonlinear coefficients. All of them can be spatially tailored by design, so we can get a function on the surface, some kind of a way to control light spatially on the surface. And this opportunity is excellent in giving us a capability to design the wavefront of reflected and transmitted and scattered waves from these surfaces. So we can, for example, scatter a uniform plane wave out of the surface, or we can understand what is the local response to have some kind of spatial amplitude modulation, or even phase modulation, polarization response. And by that, we can create all types of functional optical elements. The most famous is these flat lenses that are also called meta lenses. But we can also use these metasurfaces for holography, sensing, meteorology, polarimetry, beam shaping, and all these applications. I will touch upon some of them. For example, augmented reality, virtual reality, and so on. We can also look at the nonlinear optical interaction, where we shine intense light on this metasurface, and through a nonlinear process, this surface emits light at new frequency, and then we can also control this light at new frequency, and I will touch also upon that when I will show you how we can create metasurface-based active terahertz emitters. So just to show some capabilities of metasurfaces for flat optical elements, we can look at the case of lenses. And if we want to create flat lenses, usually we can use diffractive elements. They are really good in having flat surfaces, but one of the main problems is that due to the periodicity, they are highly dispersive. You have a strong chromatic aberration. For example, if you design a lens to focus 620 nanometer to 1 millimeter away from the lens, any other wavelength will be focused to a different distance. For example, 450, you can see that it's focused further away, and so on. So these diffractive lenses, they fit usually single wavelength application, and they don't fit more than a single wavelength or a few wavelengths or a broadband illumination. But with the metasurfaces, for example, we can use the polarization degree of freedom to print on the same surface and multiplex two completely different lenses for different spectral regime, which is something that we showed a few years ago. Now, if you look in the visible case, if you look at this metasurface, and you look under polarized illumination, you can see that it has a completely different spectral response. So you can design these different polarization lenses to focus light independently. And in this case, we show that we can use this multiplex meta lens to basically focus both blue and red light to 1 millimeter away from the surface and correct these chromatic aberrations at 2 points. But you can also extend this concept further, and we developed another interesting concept of multi-layered, multispectral, multifunctional. Because each metasurface is really, really thin, you can think of stacking many, many metasurfaces, each one with a different spectral response and maybe a different functionality, and then you, at the end, can have a composite optical element that has a complex task that is engineered, and the total functionality is basically, let's say, the summation of all the functionalities of the different metasurfaces. If we use this concept and show it for the ultra-thin diffractive lens, we can, for example, stack different lenses one after the other that control different frequencies or different colors in the visible, and then we can reduce significantly the chromatic aberrations of the diffractive lens, and also we can perfectly match the focal point of triplets of wavelengths. So we showed this in the past. This is an image of 3 different lenses for 3 different colors, but we also developed some kind of a multi-layer fabrication process. In this case, we used a consecutive E-beam writing. You can see the E-beam process of writing different layers one on top of the others. And now actually I will not present it, but we are working on developing new schemes for a highly multi-layered layer to put them one on top of the other. And here we can see how the composite multispectral lens looks like. And if we take this lens to the lab, if we look at the conventional diffractive lens, this is a measurement at the lab, and pass white light through this lens, you can see how this lens focuses different colors to different location after the lens. But you just take this off and put our metasurface 3-layer lens, you can see this beautiful white focus that is generated. And here you can see for a coherent light illumination, conventional lenses we know focuses 3 different colors to different locations in space, but our metasurface-based lens for RGB perfectly matches the focusing for red, green, and blue. We can also, as I told you, print different functionalities for different spectral regimes. So we show here the case of elements that were designed for STED microscopy, where you want to control the green and the red light differently. You want to impose some kind of a vortex on your red spectrum and focus your green spectrum. And here you can see it with 2 different types of foci, 2 different types of vortices, one with helicity of 1 and the other one with helicity of 4. And everything is perfectly aligned because this is one of the strong merits of this multi-layered, multi-functional scheme. Here, I'm not sure you see it very well, but here we create a lens that has an anomalous focusing. Instead of blue that will be further away, here we focus first the blue and then the red, so you can really design and basically fit your functionality per application. So what is it good for? One, a really hot application now that is really challenging is to create the ideal augmented reality glasses. And it is challenging because we want really challenging features out of these ideal augmented reality glasses. We want them to display bright, full-color images at high resolution, have a large field of view, a large eye box. They should be lightweight, they should be affordable and socially acceptable. And still, even though we have seen the latest augmented reality glasses out of Apple, we all know that it is still far from this vision. They are not lightweight, they are not foldable, and not socially acceptable. They don't look like ordinary glasses. But here we may try to use this meta materials or meta surface approach to improve on the metrics that we want to achieve. And our idea is basically, because this is so thin, our multi-layered approach basically treats red, green, and blue at a thickness of less than half a micrometer. This can be a coating on the glass, a thin coating on the glasses that acts as an optical combiner to project, to take this projection image and make it project further away in space. So this is the idea that we had in mind, and we started to work on showing that. We have some demonstrations, and here you can see in all the first proof of concept. I will show it in an image. What we see here is a short movie that was taken with a mobile phone camera that was held by my student. You will see here a piece of glass, and on top of that, the meta surface is printed, and we will see this green guy that is augmented and is walking in a free space. And you can see this guy walking there, and this is a very simple system that was assembled at the lab. You can see how simple it is. This is the projector. Of course, it's big, but it shows the concept, and here you have the printing of the meta surface, and we have developments on top of that. So we can do it for both for planar surfaces, but we have worked also for doing it for curved surfaces. Here, this is a demonstration on a contact lens, but we can also, we have a demonstration on big lenses, curved lenses that we can also use this technology for. And now I would like to switch gears and show you a bit how we can use these active nonlinear metasurfaces to tackle some needs that we have in the terahertz regime for terahertz technology and for terahertz waves. So terahertz waves are the waves at this range of frequencies that is exactly between radio frequencies and the optical technology. So this collision or being between these technologies basically means that the frequencies are too fast, too high for addressing them with the radio technologies, but the energy at the same time are too low to address them with the conventional optical technologies. So in this terahertz band, we still have insufficient sources and elements. We have sources and elements, but the capabilities are not as good as the capabilities that we have in the optical regime or for elements in the radio frequency regime. And there are important and ever-increasing suggestions for applications in this regime. For example, for fingerprint identification, standoff identification of material, for physical science, for early medical detection of medical cases, including, for example, skin cancer and cavities in teeth, penetrating imaging, all sorts of other medical applications, and even for art, to look into boxes that are closed. The terahertz waves can penetrate some materials that are optically opaque and so on. But there are problems, and what is the big benefit of the metasurfaces? These active metasurfaces, they are composed of millions of really tiny terahertz dipoles. Each element here is about 1,000th of the terahertz wavelength, and we can control it in space. So it's like building the ultimate material. It's like building the material one dipole or one atom at a time and putting it exactly the way we want it to be in the material. This gives us really beautiful control capabilities over the emitted terahertz waves. And our idea is usually in terahertz application, you have some kind of a terahertz source and you have some kind of a target, but you need to treat this radiation. So you want to shape it, you want to control the polarization and maybe also to steer it. And we are working on putting all these functionalities into this functional nonlinear metasurface emitter. If you're interested, you can Google this nice conceptual animation that is called the terahertz waves, the missing electromagnetic waves, and see the concept in this animation. So some taste of what we can do with that. We show that we can control really continuously the terahertz polarization in space. This is something that is not very easy to do with conventional emitters. This allows us to control it also spatially, so we can show all sorts of vector beams. This is something that is easy to do in the optics. In the terahertz domain, it's not easy to do, but with our technology, it becomes possible again. We show that we can create pure circular polarization state. This is important, for example, for medical application, for drug detection, to understand if drugs are fake or real. So we show that we can use it for circular defluorescence spectroscopy. This is an important tool in biology and medicine, and even to control for temporal shaping of the waves. So we have a lot of works on that, but don't have time to show them. This is a highly developed technology. If you're interested, you can ask me about it or reach out. And coming to the end, this is basically a picture of my group. We're interested in nanoscale light matter interaction, metamaterials and metasurfaces, and ultrafast and nonlinear optics in general. And I showed you just a bit of what we do. If you're interested, please feel free to contact me or the guys in Ramot. Thank you very much.
Thank you very much, Professor Ellenbogen. And now we will move to questions collected via the chat. Tal, can you look on the chat and address the question or questions that came up during your presentation, please?
Yes. What are the main technologies used for manufacturing those patterns, and what are the resolution of the patterns? So the main technologies that we use for the research are E-beam technologies. But now, since this technology of creating metasurface is already evolving and going into industry, there have been recent developments, and now metasurfaces can be printed on cheap size wafers. So this technology is really evolving. The resolution, even though they are a nanoscale resolution, still we can do it into really large surfaces. And sounds weird. I hope this was fixed. What do you mean by printing? I mean by fabricating these metasurfaces. So it's not like still we don't have technology for printing. It is usually some kind of creating patterns and then doing some kind of material deposition, or creating patterns and then etching. But maybe we can also call it like a complex or advanced printing scheme. These are the questions that I have. If anyone would like to ask something else, I'm happy to answer.
So, thank you very much, Professor Tal Ellenbogen, for that enlightening presentation.
Thank you.
Thank you very much. And now let me present Professor Haim Suchowski. Haim Suchowski is a professor of the Department of Condensed Matter Physics at the School of Physics and Astronomy at Tel Aviv University. He performed his postdoctoral research at Berkeley in 2014, right after his PhD at the Weizmann Institute of Science. His research focuses on exploring ultra-fast dynamics in condensed matter physics, nanophotonics, and 2D materials. He also performs research in quantum coherent control with ultra-short laser pulses and analogous schemes in quantum integrated photonics and nonlinear optics. Haim Suchowski has more than 70 articles and 14 patents. He received the Alon Award for Young Scientist, the Fulbright Postdoctoral Fellowship, and he was awarded the ERC grant for his project Mirage 2015. Professor Suchowski, I see you already put your presentation, and the stage is fully yours.
Thank you very much for the introduction. Thank you for inviting me. Thank you all for coming. So today I'm going to speak about smart nanophotonics related to the metamaterial talk that Tal discussed. So just to put everybody again on the same stage, so we know that light is combined with wave, with colors. Each colors, this is actually the ruler that we want to rule to have a distance measurement of what we want to see. So usually when we are looking with a microscope or we want to look at the environment, we have this is the lens scales, and we can see humans, we can see computer chips, you can see like human hair, red blood cells. This is around 6 micron, 6 millionth of a meter. But when we come more or less to the order of the light wave, wavelength, so this is the place that we start to have some problems. We can hardly see viruses with a microscope. We cannot see cells, you cannot see DNAs, and this is in the regime of less than half of the wavelength. This is a problematic thing because we use light as our ruler. So the message from this slide is to say we cannot see below the wavelength divided by 2. Yet people have used in the past, even though they didn't understand physics, nanostructures. Even 400 years ago, when you go to churches in Europe, you see nice windows that are colored. This is not like painty colors. This is actually silver rods that were again artists took and used them with hot glasses in order to prepare this nice colors, different colors, different type of massage to the silver particles. But only in the 90s actually we as human beings understood what happened there. A physicist understood that actually this is the size and the geometry of the nanoparticles of a silver or gold nanoparticle, metallic nanoparticle that are embedded in regular dielectric like glass or air that cause these nice resonances. So they saw that actually this is the birth of nanotechnology. And what you see in the left side here, that you know, we look at gold and we like the color, but the regular gold bulk gold is gold because it's absorbed blue, it reflects red, it absorbs partially green, it reflects partially orange, and this is why we see it as a gold. But if you take this gold, the same gold, and you put them in the size of 50, 60, 70, 80 nanometer, like Tal showed in your previous talk, and you embed it in water or in glass, what you see different colors. This is what you see in the left side, in the lower left side of the window. And this is something that actually you create absorption in different colors, and then the water is not transparent anymore, it's colored. And actually the birth of nanotechnology is around 2000, again in the understanding, but actually the birth in optics, nanotechnology, nano-optics, in the sense of structural colors is really 2006, 2005, 2006. And this is only almost 20 years old, and this is relatively young science, but a lot of people have joined this effort, as we have here in Tel Aviv and all over the world, and can create with, like Tal showed, structures on the electric or holes inside metals. And this is something that you see from the like literature, or this is what we see in our lab, that you put different colors and then you can create them. Also, we didn't invent this one, but once we understood as human beings that this is there, so when we looked on animals and some natural structure, we saw, scientists saw that actually some of the colors that we think are colored because of pigment are not really pigments or chemicals. They are actually because of scattering of light and interference of light in the nanoscale. And this is this butterfly. Also, if you look on, the colors that you see, from other animals, they can change color, not because they have different pigments. You can change them just because you change periodicity to random. So this is it. But what I'm going to say now, and to speak about it now, is about the way that we, as scientists, want to calculate and to understand what will be the colors of what we fabricate in the nanoscale. And when we want to fabricate something, or we fabricate something, let's say Tal wanted to fabricate his own nano lens, so he did a geometrical structures in his where it was ovalic or a sphere. But if you go to something more complicated, you can really solve it, but it takes time. You need some heavy numerical tool that solves really the Maxwell equations inside the materials. There are some effective medium theories. One of the heroes is actually emeritus in Tel Aviv University, Professor David Bergman. And actually, but sometimes effective medium theories is not enough. You need to really go and solve the Maxwell equation in each point in space, and then sum them together in the place that you want to see it, let's say in our eyes or in the camera. And this is a process that you need, again, heavy machinery, simulation tools that take you more or less. Here you see the structure, and then you see in the right-hand side, you see the wavelengths. Each point of this wavelength can take you sometimes several minutes in different polarization. It takes time, but it's still doable. But this is what we call the direct path. Take the geometry and then understand, calculate what is the let's say colors that will be emitted or absorbed in this material. But most of the time, what is important for us is, or the one that want to invent some machines or some tools with this nanostructure, they want to understand, okay, I want this glass to be in this color or in a summation of specific colors, and I want it to look like this. What is the geometry that I need to put in? So this is what we call the inverse problem. So designing the nanostructure geometry in order, on demand, in order to have the right spectral response. And actually, there is no time-efficient solution to do this complex tasks. It's really something that you need to do trial and error, and it takes sometimes days and weeks, because you try and then you calculate and you see if it's good or bad. So this is what we call the inverse design. Just to give you some again like highlights, let's say that we have the design feasibility, a very high. This is the y-axis and the spectral complexity. So there are some analytical solutions, like I told you about the effective medium theory of David Bergman and all others, that you can do some analytical solution. This is very high design feasibility and actually can be done, but it can be done for very simple structures. If you take some more complex one, sometimes they are more or less what we call semi-analytical. let's say we have this U shape, and so U shape is more or less like a bar, like an ellipsoid that was a little bit squeezed. So more or less the same results can be there. But if you start to take some other stuff, numerical tool, you need, even something like the letter H, you want to say what will be the response, the spectral performance, something like this with different arm length and angles. This is really complex hard problem, and you need to do some trial and error or to go to the stochastical parameters or numerical tool. What we did here several years ago, we were the first one that actually suggested to use deep learning, more or less 2015, 2016, to take deep learning, deep neural networks in order to solve this problem, not only from the optimization part that was around for a specific structure, but to do like a real network that will solve it. And what I'm going to tell you today is our several articles and several articles here and some of the patent that we have from this research work. So again, what we did over here, so first of all, we designed like the letter H that actually if you have even this letter H, which is very simple one, and there are many others structures, but even the simple ones have more than 2 billion different spectra that determined by the length of the leg or the angle of the leg or the size of the structures, and if one leg is appearing or not. And what we did both, like this is also was the first time that people have implemented the bidirectional network here. We did both the inverse and the direct in this network, what you see over here. So we have the, let's say the inverse design, then we think this is what we want to have. This is the structures, and then with these structures, we test our results with the forward network and test our inverse design as well. Practically what we did, this is actually the real network. It was in the beginning, we have the material properties. What is the polarization from, what is the response in different the two polarization, the vertical and horizontal, and in different wavelengths. And then we did several layers that are group layers, then joint layers together. And in the end, what is the right, like a finite number appearing, not appearing, one of the leg, and what is the angle. And from this, we had some loss function. With this loss function, we also take the results and also did the forward design, even though we can go and do it with the numerical tool, but usually numerical tool take around, again, 10 to 20 minutes. So in this case, we did it again with a network that took, let's say, several microseconds, so milliseconds here, so it was quite fast. And we, in the end, showed if the end result, we gave it also a loss function here, and we summed them, the loss function in the middle and in the end, to really optimize our network. I won't go into the details, but it's really in the articles. Also in the articles, we in the first article, we put all the code there, and you can play it with yourself. Just to show you some, we did it in the first time, 2018, 2018, but also we were the first one that did it experimentally. There were many group work later on that did it in theoretical and the numerical tool, but we wanted to go and did it in real life. So we fabricate this H shapes. The fabricator didn't tell the dimension to the one that did the network, and then we wanted to see if the network, if the neural network can really determine, and actually what you see over here, that the deep learning prediction was very, very close, even though it was exactly perfect, and there is a meaning for imperfection, but if you run the result of the deep that actually the data is is a non-linear, it's not a one-to-one correspondent. There are several solutions that can get you the right answer, more or less. So plus minus, as you see here, 15 to 20 nanometer resolution and plus minus several degrees, but it's good enough. And this is, again, was in less than 1 second, instead of waiting 2 weeks for trial and error. We also continue to do and to predict what is the resonance for specific molecules. Some of the molecules, chemical molecules, are real molecules, or if we took it as a synthetic one. This is very important. You'll see later on about the application for doing like amplification to sensing. So usually you want to maybe determine or to sense a specific molecule, and maybe it's very, very sparse, so you don't really catch one of them. So you attach a nanostructure like this, and this is acting like an antenna or an amplifier to the molecule. And this is, you need to really design it to be in the same resonance structure of the molecule. And what you see over here, that this is a design of the molecule that have more or less the same resonance structure as the molecule. This is, again, important to chemical sensing. And sometimes, you know, when you do neural network, the guys in the computer science say to you, you know, maybe let's see if the network learns something new that you didn't train it to. And this is something that we did as well. So we didn't train the network to understand what will be when there is no lag at all in the nanostructures. And actually we put a flat response, and actually the network managed to really see that there is no spectral features. So the reason is that there is no lags over here and there is no resonance over here. So this is another advantage, again, that we saw from this network. Later on, after us, many groups around the world did it in different realization of nanostructures, shells, and different surfaces and different arrays, and actually different structures, not only the letter H. Actually, you'll see in a minute, the letter H is very, very difficult compared to others' configuration, but we didn't know this back then. And yeah, so and now we are again cited more than 500 times, so it's nice to be the first. Later on, what we did, we actually, as deep learning neural network has advanced a lot in the last 6-7 years. So the next thing that we started to do is to really say why to take the letter H and not to take images of what we see, and maybe to take a lot of other structures, geometry. As I told you, geometry is the one that really determined the spectral response. And actually, back then, there was a new scheme that based on what it's called peaks to peaks, a conditional GAN image to image that's like a translation network that actually can be trained on, as you see over here, on very sparse information. And then when you trained it on map to map realization or image to image, as you see over here, you can really maybe understand some new stuff or give more information. So we took it and actually did it to the 2-dimensional. We called it, instead of peaks to peaks, it's a 2-dimensional to 2-dimensional. We called it a spectra to peak. Also, the spectra was actually embedded as a image, and we could actually we did another network, Itzik here, the student of Lior Wolf, and actually the prediction was we trained it with the data that we had and more data that we generated, and we could see that there is this baseline. This is real information. This is the ground truth, and so we started with this one, and this is the ground truth. And actually, the network found it as an image, as a pixel size, which is also very important to see more than just the letter H. And also we fabricate this one, and we managed to show that it's working. So I'll go into the details. What it's good for, in general, nanostructures and metamaterials are very important to a lot of stuff. But when we want to do this stuff, this let's say idea that you have, you need to design what is the right structures as compared to the spectrum. So one of the important, let's say, application is increasing the solar cell absorption. So usually we use a silicon. Regular silicon absorbs more or less 11% of the light that you can. But the question is, can we do more? Every 1% is very important to the efficiency of the solar cell panel. And actually, several years ago, a lot of scientists went to this direction. And this is a report from Kyoto University that actually this kind of sizes can absorb more than 40%. This is a laboratory, of course. But if you take a regular silicon and you want to really do it efficiently, you need a specific structure. So this is something that a direction that we can go to. Also, what we call like nanomedicine. This is also from Rice University several years ago, that you wanted to do cancer phototherapy. So with the photons, so you have a cancer cell that is bad, and you can take these nanostructures and put DNA that is complementary to the cancer cell, and then you inject it to your blood, and it can, when this DNA reach the solar cell, the cancer cells, it's attached there. Here you see in the right-hand side, you see the nanostructures is waiting inside the cancer cells, and then we shine light, and if it's the right color that absorbed in this light, in this case, it's a nanosphere, so it's easy. But actually, you heat it to more or less 1,000 degrees Celsius for very short times, and you kill the cell. So this is, again, something that's connected to the ultra-fast and nonlinear phenomena of these structures. Also, again, in this field is what we call cloaking invisibility. The reason that we don't see behind our so it's because there is a light is doing scattering, and the scattering is always in one direction. But if you want it to be in the other direction, that it will be bent to again to your eyes. So what you see, you need to do, you need to put this metamaterial. People have done it in microwave, and really recently, more or less 10 years ago, 9 years ago, in optics in Berkeley, where I was a postdoc, not by myself, but my colleagues. And when in optics, we can do fabrication less than tenths of the wavelength, we can also maybe do it. Then we can do cloaking invisibility. So just to summarize, we introduced for the first time a novel deep neural network architectures to really do inverse design of nanostructures. We showed that it's fit very well the numerical and the experimental results, and also expanded to spectra to peaks. The neural network, and I would like to thank my colleagues from the computer science, Professor Lior Wolf, Itzik Malkiel, that work on this, on my group, Dr. Michael Merejan, that led the project with the other students and other students that work on different stuff in my group. So thank you very much, and I'm ready for questions.
Thank you very much, Professor Suchowski. Now we will move to questions collected in the chat.
So can inverse design be used to locate spatial resonances such as SLR surface lattice resonances? Yes, of course, you can do it. This is something that actually our joint student of me and Professor Tal Ellenbogen, that is now in Caltech, actually work on the surface lattice resonances. And if you do some training on different length between structures, the pitch one, you can really also find the right location with surface lattice resonances. Yeah, so the quick answer, yes. Sometimes, you know, there are analytical tools that can find it easier, but in the general case, you need this optimization or deep learning neural network. In cases where the structure suggested by the inverse design is difficult to fabricate experimentally, in that case, what do you suggest? So what is nice about this thing is that when you go to inverse design and you teach, you need to train the neural network in different realizations. So sometimes you get solution that you didn't expect. And as I told before, it's a non-linear problem. It's not one-to-one, so there is no a single inverse design. So sometimes you will get several capabilities, and you can rank them. And some of them that you cannot really fabricate, you go to the other one that maybe you can fabricate. Second answer is that you can put the constraint, and this is something that we do in other inverse design research that we do. We put the constraint of the fabrication inside the training data, and then we get solution that can be fabricated. So let's say we cannot fabricate something less than 20 nanometers, so we put a constraint. You won't get in the trend in something that it's less than this one, or there are other. Yeah, what is the difference between optimization and deep learning for the design of nanophotonics? So this is a good question. This is sometimes people think that, okay, optimization have been around like 40 years. So what is the new stuff? So optimization is, yeah, it was around. There are many stochastic algorithms, but it was good for one target. So I want to have a specific one that emit in red. But if you want to have many questions for many users, so you need to have a network, and then you can find the hidden rules, let's say, for the arrangement of different stuff. So instead of usually optimization, you can do it. So it's take you also several, let's say, days to find the right optimization algorithm, but then it's good for one solution. And then you need another several days for the different solution. Network, once you have a good network, so you get the information back in less than 1 second. And what is the saving of time that you can achieve with the nanophotonic deep neural network? So I already told it in short. So instead of trial and error for several days to 2 weeks, let's say when we fabricate something, it's not exactly what you wanted. And it's take more or less several days, really, several days that you say, okay, I wanted 200 nanometer, but it was 190 nanometer. I measured it with the AFM, but it's not exactly what is happening in the reality, and there was another layer. So it's take you several days to a week, and here you can get it after you have a good network, again, in what you are trained to, you get it in several seconds, let's say, minutes.
Okay, thank you very much, Professor Suchowski and Professor Ellenbogen, for your compelling insights. Thank you, everyone, for attending our virtual event today. Should you have further questions or an interest in collaborating with Ramot and Tel Aviv University regarding these inventions, we will be delighted to explore the opportunities. We also plan to send you by email the link of this recorded session, which might be needed for your further steps. Have a nice day, and thank you very much.
Thank you.
Thank you.